Hey, welcome back. It's been a while. Today we're going to discuss a new topic called momentum. We're going to be describing the kinetic and potential energies of macroscopic objects and use measurement to develop an understanding of these forms of energy. Today we're specifically going to talk about momentum. Well, momentum is the product of an object's mass and its velocity. So what that really then tells us, the word product means we're going to take the mass times the velocity, so that's our equation. Now the hard things for students to remember is P stands for momentum, and then it's the product of mass and velocity, so mass times velocity. Here's examples of it. We've got a 100 kilogram linebacker moving 10 meters per second. Well, let's not make it harder than it is. Momentum is mass times velocity, so it's the mass, 100 kilograms, times the velocity, 10 meters per second, and we get an answer of 1,000. And now our units are, there's no special units for momentum. We just put them together. We take kilograms times meters per second and get 1,000 kilogram meters per second. In this one, we're supposed to find the momentum of a 20 kilogram dog moving 4 meters per second. Well, his mass is 20, his velocity is 4, so his momentum is 80 kilogram meters per second. That's momentum, people. Okay. Momentum is used in collisions. We have what's called an elastic collision. Elastic is when the items are going to bounce off of each other. I may have cut that off. Elastic is when they're going to bounce off of each other. An example of an elastic collision is a ball and bat. They hit, bounce off each other, and keep going. Another example is inelastic, and this is when they stick. This is a bug and windshield collision. Right? These are types of collisions, and these are used when we're discussing momentum. Today in class I'm going to give you an example of two marbles colliding and relate this to an elastic collision. Okay, there's a force and momentum relationship. There's a way that, and we've talked about momentum a little bit, and some students have wanted to use that terminology, and I've told you to resist that, but now we're going to talk about momentum. If a boxer hits another boxer in the face, what happens? Well, the boxer who just got hit, his face gains momentum backwards. Why? Well, the momentum from the fist is transferred to his face. All right, he gets momentum. The fist had momentum because it had massive velocity. It hits the guy's face. There's an elastic collision, and that momentum is then transferred to the guy going backwards, his face going backwards. Does he want the collision to last for a short or long time? Well, we want the collision to last for a long time. The longer you hit somebody, the more damage you're going to do. For example, if I hit someone in the face with just a small little jab, and it has a very little time, then they're going to have little momentum. If I hit them for a long time, if I really try to make that punch last, it's going to have a much greater change in their momentum. So somehow, force and momentum are related, and the way they're related is by time, and that's called impulse. Some of you may be saying, well, how is that? Well, impulse is a change in momentum. Impulse, as we're saying here, is a change in momentum. All right, and you hit someone, if you're boxing and you hit someone in the face and you make their face go backwards, you've changed the momentum of their face. Their face had no momentum, and then you made it go backwards, so it had velocity, so now it has momentum. Well, impulse then is also equal to, this is key, it's also equal to force times time. The punch is thrown with force and for some length of time. We said if you make it longer, you're going to change that momentum even more. Alright, so we want to have maximum force and maximum time for maximum impulse. So what this allows us to do with these two equations, because they're both impulse equations, we can take the PF minus PI and set it equal to Ft. And this in general becomes our impulse equation. Right? This in general will become our impulse equation. So here's an example of impulse. A 200 kilogram car hits a tree going 5 meters per second. This is impulse because, as you can imagine, when a cart hits a tree, the cart stops. So the tree applies some type of force because it causes it to decelerate, according to Newton's second law. So there is a force. There's a collision lasts for a certain amount of time, and there is a change in momentum. So let's calculate these. Find the initial momentum. Well, the initial momentum is the mass. The initial momentum is the mass, which is 200, times the initial velocity, which is 5 meters per second. So we get an initial momentum of 1,000 kilogram meters per second. Find the final momentum. Well, it's still going to have the same mass, so it's still going to be 200. What happens when a cart hits a tree? Well, the cart stops, so the velocity is 0. It says calculate the impulse. Well, this is subtract the two knuckleheads, as you can see here. We're going to find the momentum, find the impulse. That's the change in momentum. Well, the final is 0. The initial is 1,000. So it's negative 1,000 kilogram meters per second. The last step says find the force. Find how much force the tree hit the cart with. Well, we've already did this part. That was right there. So I can, and we know the time is up here. So I can simply say F times 0.2 equals negative 1,000. Divide by 0.2. And we find out the force equals negative 5,000 newtons. Some of you may be asking, why is it negative? We'll discuss that today in class. I'll catch you guys on the flip side.